All right.
Hello, everyone. Sorry. Okay, hello, everyone. Good afternoon. It's time to start our today's Astroph. Today we have three presenters, Angel, Priyanka, and Betty. Who wants to go first? Priyanka, thank you. Can you remove that? Okay. So, very quickly, this paper is actually one of the three papers I'm going to present, like in the next archive for meeting. The idea of these papers, in general, of these three papers, are to solve the evolution of the shape of the galaxies or the size of the galaxies. So, what we know from the previous literature from HST data is something like this. So this is one of their major results, but this is what we already knew. There is a decline of size of the galaxy with the redshift. So as we go to higher redshift, the sizes of the galaxy reduces. But the question is it like an evolutionary thing, or is it like because an observational bias? Um, so what they are doing is they want to see, first of all, that the size evolution. And the second thing is to see whether this is an effect of cosmological dimming or whether it is a true cosmological effect. Till now, we had only data from HST, which was limited to redshift less than 3. But now with JWST, we can go to beyond redshifts. And why is that? Because of this plot. So if you see, now they can choose the rest frame wavelength, which is basically this window, zero point 0.4 to 0.8 micron. They can choose an optical for various JWST bands. So suppose till redshift 1, they only choose F115 filter, and so on and so forth. So they have around 1,300 galaxies from Sears data from JWST, and their photometric redshift is calculated from EASY, and their sizes are calculated from GalFit. They fit the galaxies themselves with a single Cersei profile. Let me show one of these examples. So these are the galaxies. So you can see a redshift around 1.8 galaxy and then around redshift 8.1 galaxy. Also, they have taken into account if there is like a blending, like in this case, so like this. So it fits simultaneously to both of these galaxies, removing the blending part as well. And these are so they also tested it with IMFIT, so just to see if the GalFit is doing a good job or not. Okay, so maybe I can just go to the plot. So this is the first result of the paper where they find that the RE decreases with redshift, and it is true for redshift even beyond 3. This is the other works, which is very consistent. What they also find is that when they divide the sample with Cersei index, so if they divide the Cersei index less than 2 and greater than 2, so the greater than 2 is more like elliptical galaxies. So they find that for the most of the galaxies below redshift 3, so like this one, they are you see there is a morphological difference between now below redshift 3. So the red and blue points actually diverge below redshift. So what the Hubble sequence which we see is actually happening at redshift 3, and that's why, because till HST we only had redshift 3 data, so it was always thought that this continues. But now with JWST, what we see is that it's not the case. The Cersei profile or the elliptical galaxies or spiral galaxies are sort of equal sizes. They also plot the Cersei index with redshift, and I think this is again an evidence for that you see this bifurcation at redshift around 3, and beyond redshift 3, the Cersei profile of the quiescent and the star-forming galaxies is sort of similar. They also had 470 galaxies which are visually classified. So let me show that plot first. So this is the plot if they choose I mean, they visually classify 470 galaxies, and they also find a similar pattern except for the spheroids. And the spheroid seems to have like a constant Cersei's index, but that's also because they have large error bars. The other thing which they find is the radius mass relation. Again, the radius mass relation holds up to redshift 3, but beyond that it breaks. So basically what they mean is that at redshift beyond 3, there could be galaxies which are smaller, but they have very small mass as well, or larger mass as well. But below redshift 3, it always follows that the smaller the galaxy, the less mass, or the vice versa. Another result which they found is that they find that when they plot the radius with observed wavelength, that so basically the galaxies appear more compact when at redder extreme. To understand this, what's happening is that at redder wavelengths, we are basically seeing the older stars. So the older stars are centrally concentrated, and that's why the size actually reduces. So that's what the inside out theory is, and basically it follows that. And the other thing, as I was saying, that whether this radius evolution with redshift, is it effect of cosmological dimming, or whether it is true? In order to test that, they use simulated galaxies. So they simulate the galaxies from redshift 0, they measure the Cerseic index and the radius, and then they shift these galaxies to a higher redshift and then measure it again and see whether the radius and the Cerseic is same. So this is what the plot shows. So if they use the simulated galaxies at low and high redshift, the same galaxies at low and high redshift, they see that there is no evolution. So that means that it's actually a cosmological evolution rather than the cosmic. I think that's it. That's what they have shown. So yeah. Any questions?
Thank you, Priyanka. Is there any questions or comments to Priyanka? If no, we can move on to our next presenter, Angel.
Okay, so all right, so this is the paper that I'm going to present today. And so basically it's trying to, these people are trying to find the star formation rates in quasar host galaxies with the O2 line. So basically they're, this is important to figure out, understand the coevolution of supermassive black holes and the galaxies, but there's, still a lot of uncertainty in there. And so let me hide this. So the thing with this paper is that, when we try to find star formation rates in these quasar galaxies, host galaxies, sometimes that is hard because there's a lot of interruption or contribution from AGN that contaminates the emission, right? So we have to figure out how to decontaminate our signals. Even common tracers like H alpha or UV are guilty of this. And so that's why they use A2 because, O2, because O2 is known to have not be very affected by AGN. So yeah, so here they say, oh, what is that? So here they use the O2 and neon 5 flux ratios to have sort of like a diagnostic differentiate between AGN activity and star formation activity. O2 is not very prevalent in AGN, but is prevalent in with star formation, and the opposite is true for neon. Neon 5 is very prevalent. I think it's a broadband line, so it's very prevalent in these high density AGNs. Okay, and so one of the things that these people do differently, because this has been done before, but one of the things they do differently is that they use something called Markov chain Monte Carlo analysis to basically differentiate, separate the components of their emission lines, right? So they separate the narrow component, broad component, very, very broad component of these emission lines. And so what that does, it allows us to pinpoint, okay, this line is, how much of this line is being contributed by AGN? How much of this line is being contributed by star formation? And so when doing that, they can pinpoint, they can get a more accurate analysis, a more accurate results on what the line is telling us. Is it telling us that there's more star formation rates? Is it telling us that there's more AGN contamination? And so that is basically what they do. And so here they have the results. So the O2 and neon flux ratios associated with the narrow component is substantially high at 7.86, whereas the broad component, or the very broad component, is much lower, so at 0.18. So this is basically saying, okay, the narrow component, when they finally separated the narrow components from the broad components, they saw that, okay, in the narrow components, we have, there's a lot more O2, right? And O2 is usually found is a tracer for this star formation. And what is it? And when they analyze the same flux ratios, but with the broad components, they saw that this ratio is a lot smaller. So this broadening is caused by the AGN. And so basically, this is just saying, okay, so we can get more accurate analysis results by separating these narrow and broad components of our lines. Something else that they did briefly is that they look at the flux as of, the star formation rate as a function of luminosity, and they saw that it increases as a function of the total luminosity. I'm just pointing that out because it sort of relates to my paper, where I say that star formation is more dominant at higher luminosities than AGN. And so, okay, so they just list the advantages of this, of separating the narrow components to the broad components to get more accurate results and to eliminate any AGN contamination when calculating star formation rates. So yeah, that's my paper. Any questions? Yes. Yes.
It's not a question, actually, it's a comment that I think this, whatever they have done, has been previously well established.
Oh, really?
Because O2 has always been used as a proxy for star, like the stellar component.
Right.
And also makes sense because you see near the AGN, the lines would be broad because of the mass, and so if you use the Virial theorem,
right.
So then based on the mass of supermassive black hole, then your velocity of the lines would be broad. Right. But for O2 line, because it's come from the stellar part, or basically the narrow part, the agent dominance is less.
Right.
And so that makes sense. So whenever you use a spectrum for AGN, you always fit narrow and broad components to the lines in order to differentiate that what is coming from the galaxy and what is coming from the AGN. I'm not really sure what they have done new, because even the star formation and the luminosity is correlated, is also well established.
Right.
But and also they use FDSS data, which is again what they have already done. And I know the authors, especially USO, he has already done so many papers regarding this.
Okay.
So I'm not really sure what's new in this
Well,
paper.
when I read it, they made it seem, they made it seem like very,
Yeah.
wow, look at
Wow.
this new, we are eliminating AGN contamination and
Yeah.
we are getting much higher quality results.
Yeah,
That is the vibe that I got from this paper. But thank you for letting me know.
Yeah, I think it's well established. So probably maybe we
Maybe
are
they're
missing
exaggerating.
something. Yeah, or maybe we are missing something which they have done.
Maybe.
Because it's a published paper. So it might
Yeah,
be
yeah,
something new. Yeah.
Okay. Thank you.
Okay. Thank you, Angel. Any other questions or comments to Angel? If no, we can move on to Betty.
Okay, and this is an interesting paper that I found that use transformers to detect FRP. So last week I think many people are talking about CNN, and I think CNN has I think not really good accuracy, or F1 score is like 60 or 70 something, and I think maybe there could be some method to achieve better like results. So for this one, it uses transformer-based multi-text model to detect phase radio bursts without requiring computationally expensive desperation preprocessing. So it includes some preprocess and also achieve a really good result, which has everyone scored 97.8, recall 95, and the precision really high. And I think the false positive is like 0. And also it can reliably estimate dispersion measure and time of arrival, which has the data in this paper. So okay, and these are some of the best part of this method, like multi-task learning and automatic simulation-based training. It uses simulated data, it has the observed parameters, and it can generate some simulated data to help training. And also it has high interpretability and workflow integration. And also it allows a petabyte scale validation, it is largely easily to verify. So this is the method that it uses. It uses supervised classification for FRI discrimination. So the reason why it don't use the weird data to mark as FRB is it is really likely to mismark if you simply use that method. So it still requires a supervised classification, and it also uses multitask unified inference and simulation driven generalization. So if you're more interested in the structure, it can read this. And the architecture contains 3 parts. Like a Y structure, and the part including the transformer and also the patch classifier, okay, and transformer encoder, something like this, to structure the the model. And here. Oh, here it talks about how the FRV simulation is generated. There are some parameters. Oh, and this is the structure of how it is generated. It contains it's generated by simulator, including the simulated dynamic spectrum and related outputs. And here are some of the parameters that it used here. And So this is basically how it is generated, and let's go to the results, like the table. Oh, so here it is a result, and this divided by 402 is a resolution. So like if you make this m higher, it might make the like time consuming shorter. But actually, the result is quite not large. Well, not with large difference. So if you care more about time, you can like higher the m, and you still have same quality of results. So you can see that this is a method that I think maybe I previously used, which was like not that good recall or F1 score. But here, if we use this method, the swing why not, we can achieve a 100% precision and like 95% recall, and the false positive rate is 0. And here are the dispersion measure and theory, and it uses like processed to fit to achieve a better error. So it's a result, and you can see that it is much better. Like it is quite good, as you see in the like the fitted data. And this graph excludes some of the outliers already. So like the falsely detected is not shown on this graph, and you can see that from this graph, figure 6, there are some poorly fitted parameters when the FRI are like strong. So this method might fail if the FRI are like too large. So this method is not to replace the traditional method that we used initially. So it can use like as a substitution or just to use with the traditional method. Okay, but like, as we can see, you might think that the advanced score, like the false positive rate, is like a little bit too low or like strange, just because that the data is kind of limited. I'll go to the problem part. It's here. Okay, some limitation of this. Like, there are some limitation for the simulation pipeline. Like, it is, I think it's measured in a real world condition, but it is like kind of restricted. Like, they only use like the data they observe in one specific place, and also one like telescope that they use. And if you are like trying to detect other on other telescopes FRB, and you have to train again. But that method will be quite similar, so it is easy if you are trying to like create another model to fit other telescopes. And there are some sampling constraints, as I said. So it is the simulated like the parameters and the locational sensing is kind of restricted. So this is kind of some of the problems that this research met, but still the result is quite decent. And if there are like more data to verify the method, it could help like accelerating the detection of FRB. Is there any question? Really?
Hello, Betty.
Hello.
Betty, I want to ask a question.
Okay.
So this is just a simple question because I don't know. So the first thing, because it's talking about FRP, then how how the machine learning understand this is FRP or not? Maybe you need a
Oh,
physics guided or something. And the second question is how to choose the loss that described in the paper. I mean the loss.
Yeah.
Like there is a MSE loss, focal loss. how they decided.
I think they didn't mention about loss much. I didn't talk about loss much. And for the FRV detections, it is basically like supervised method, and yeah, they use deep learning and like binary classification, like there is or there is not FRV, and I think there are like more details in this paper, and I didn't go like deeply.
So it's not related with equation. It's not related to equation 1. No.
Oh, the equation 1 is, I think it's about I mentioned about the post process of fitting for the dispersion measure, and equation 1 is the the fittings equation, like to do the fitting, to how to do the fitting.
Okay.
Yeah, and it is mentioned.
Thank you.
I think it's mentioned in like under table 5 and like figure 5, but I cannot find it now.
Okay.
Yes. So here, these are two ways to estimate DM value. The first is direct output from model DM text, and second is obtained by equation 1.
Okay.
Yes.
Okay, thank you, Betty. Is there any other questions or comments to Betty? Okay. If no, we can decide on tomorrow's presenter for. Oh, next week. Sorry, next week. Changwen is already volunteered for next week. I don't know.
So I cannot do on Tuesday.
Oh, okay.
So next week.
Okay. Any other volunteers? Good. Thank you.
Terry will. Terry will go.
Yes.
So I said then they can only nominate the other people.
Okay. On Tuesday.
Terry, you can circulate by writing a notes.
Yes, Darian.
Hi? What?
Darian.
Me?
Are you
No.
volunteer?
No. In Wednesday. It's fine.
Okay, then I'm volunteer for Wednesday.
Yeah, Wednesday.
You can put
Okay.
Tuesday because people are there, so you can just put it.
I volunteered again, and one more. Okay, I will put it.
Yeah.
And okay, thank you for your attendance. See you next week.
Thank you. Bye-bye.
Thank you. Bye bye.